Good afternoon and welcome to Stamping Out the Bad Parts Optical Metrology for Sheet Metal Applications. My name is Yanni. I am the Technical Account Manager and Argus Expert here at Trilion. My background is in tool and die and automotive manufacturing, and I've been helping companies and universities with this state-of-the-art optical measuring technology and how to implement them perfectly. So I've been happy to help industries like aerospace and automotive and biomechanical. And with me today is my colleague, President and Founder of Trilion Quality Systems, Mr. John Tyson.
Hello, I'm John Tyson. I've been in the industry for more than 35 years, expert in a broad range of optical metrology methods, and we're very pleased to be able to provide this technology to the automotive industry. Our team is located primarily in Philadelphia. We have offices in Detroit and in Seattle, and we do everything from engineering services of a lot of the technologies we'll talk about, as well as provide advanced training and user group meetings, workshops, that kind of thing, at our facilities and in all the different cities. So we have a number of different technologies we work with. They are from GOM, the company for optical measurement, and our primary tool for strain measurement is our ARAMIS technology, and where we're using a stereo imaging pair to be able to measure full field deformation, strain in materials and do vibration analysis. Our Argus technology that Yanni will describe in good detail is our formability analysis tool, and this is the premier tool in the industry, and we pretty much have all the OEMs in North America rather, and providing quality analysis of formed parts. Our tri-top utilizes the same kind of concept as the Argus, but is used primarily as a large-scale CMM tool, a portable CMM. And so we can walk around large structures and be able to capture the coordinate system and 3D coordinates of components and use that for alignment of ARAMIS and ATOS measurements. Our GOM CT is an advanced CT measurement or computed tomography X-ray system that allows us to measure the inside of parts with incredible detail. It's the highest precision CT system in the world. And then our ATOS systems are used for 3D scanning, shape measurement, and be able to look at the dimensional characteristics of parts. We apply all of that as engineering services. So our optical metrology bridges the gap between testing and simulation. Traditionally, we are measuring displacements, vibrations, and strains, and we can do that traditionally with methods that use single point sensors and everything from LVDTs to accelerometers to strain gauges. And we're using that to be able to validate complex computer models. And with these complex computer models, the idea of being able to use a full field imaging technology instead of single point sensors allows us to fully visualize the strain fields, displacement fields, and vibration modal analysis of parts very simply and easily. So we'll be talking about using ARAMIS for material properties. That includes the material properties done by the material makers, providing you a forming limit curve using typically Nakajima testing, but also the idea of being able to improve the accuracy of your materials, being able to do incoming inspection, lot inspection on your rolls of material, doing a tensile test to get the end value, and using that to get you corrected finite element forming limit curves with using the end corrected forming limit curve and correcting it also for nonlinear forming behavior of the forming test. We can then, we use a patterning method instead of circle grid analysis, we're going to be putting dots on the part, either using chemical etching or our new laser etching capability. Then when we get into Argus measurements, we're utilizing Argus for formability measurements, and the criticality there is being able to then do precision measurements with FEA analysis, and then next generation FEA analysis utilizing nonlinear forming characteristics is going to increase the precision of the measurement and the analysis so that they're critical. We can then use the scan box to create high precision measurements, which is part of our Industrial 4.0 formability package. We also use ARAMIS high speed for press deflection, so we can understand how the press is moving and be able to report on it from both low and high speed measurements with various materials and various tools. So ARAMIS is a stereo imaging sensor where we can utilize a pair of cameras, just like our eyes can see where something is in three-dimensional space, but we're doing it in a completely non-contact, full field way with a precision of the stereo imaging to be able to directly measure 3D shape, displacements, and strain on everything from a micro scale to a large scale, and be able to do this from static measurements to high-speed measurements, and particularly for FEA validation and modal analysis. And here, so the ARAMIS is able to see the full field characteristics of the material and be able to get true measurements on there with very high precision, and allowing your incoming material to be corrected, correct the supplier forming limit curve for this material's actual characteristics, and also for the non-linear forming behavior done by whichever test was appropriate in this case. And so the material properties are just automatically calculated for you in a very nice and clean way, an autonomous way. And so material testing becomes a full field method that allows you to truly understand the material properties. NASA Glenn has shown that they have better material properties on all their materials, not only for polymers and composites, but specifically for metals also. And we can calculate your material properties automatically. So all the parameters that you would normally want to collect, you just put the part in the machine, hit the go button, and it calculates all those material properties for you. There's an example of just pushing the go button, and the system automatically calculates your material properties, and will then transmit those material properties right to the Argus system. And now we'll talk a little bit about what your material supplier does from a formability curve measurement perspective. Yanni, why don't you take the head on this?
Thanks, John. So as John mentioned, we're going to be talking about the ARAMIS for Bulge testing, Nakajima testing, or Marciniak testing. The great thing about the software is that now it has an automated and integrated suite of tools that will take the measurement and cut the sections and get you all the measurements that you need. You'll notice here that this is the forming limit curve that it is creating, and typically what we're looking for is, as we see here in points 1, 2, and 3, we see the uniaxial strain at point 1, we see the plane strain condition at point 2, and at point 3 we see the biaxial. What the system does, as I mentioned, on the specifications of the ISO standard, you run different specimens and the system will automatically cut the sections and export them out into our sequence and then kick out a forming limit curve. So this is great for understanding the material that is coming into your facility all the time. And this is an example of that standard, which is the ISO 12004 section-based method. What you're looking at here is the 3-section method that are about 2 millimeters apart. You'll see the major and minor strain at the top of the screen and the sections cut at the bottom. From here, the system will automatically export this into the module that's included within the software and do all the measurements for you and then spit out the forming limit curve, which is really great and really fast. And this is an example of how it draws that parabola in the major and minor strain and the points that it's using based on the ISO standard. And this is taken automatically. All you need to do is run the specimens, which again is an automated form from the reporting side, but the system does everything after that quickly and efficiently. And here's another example of the forming limit curve that it creates. You'll see the black dots on the actual graph, which signify the different samples at that same point or the same width of specimen during a Nakajima test, for example, for biaxial, plane strain, and uniaxial strains. So the benefit of all this is that you get the material characterization for the formability. This is going to benefit you during tool tryout and production monitoring, so you have the same forming limit curve or the correct forming limit curve for that material that you're using, which is crucially important as we've all done spot buys in the past. You have questionable material at times and you really need to understand fully what is going on. But you'll notice here that we can support the industries such as for steel and aluminum suppliers, the automotive industry, and the consumer goods industries. John will now kind of go over some summary of what we just discussed here. So John, I'll hand it back over to you.
Thank you, Yanni. Using ARAMIS for automated incoming inspection really provides the much finer material properties, which are crucial to every step of the measurement process. Our system automatically has the templates for every measurement that you would need to run, and so it just runs all the steps in a pre-programmed way. So it makes for a very clean measurement for the operator. It also automatically corrects the incoming forming limit curve for the end value of the specific material that's incoming, and also for the nonlinear forming characteristics of the Nakajima test that was used. So this gives you perfect forming limit curves for the specific sample of material that's coming in, and really leading to more accurate material properties, and really allowing you to provide the best information for incoming material measurements. Yanni?
Wonderful. So now we're going to go over the Argus system, which is some of you might typically use this on a day-to-day basis for sheet metal formability, but we're just going to go over and what it all means. So the Argus goes over the deformation analysis in sheet metal in the forming industry, and some of the benefits of that is that you're going to get the material deformation analysis, you're going to detect critical areas on your form parts, you're going to see the localized and overstretched areas, which basically means that you're going to see the whole part's response to the forming process, and not only to the forming process, but through each station that you're running, not just the draw, maybe the restrike, maybe the final trim to see if there's any oil canning happening. Now, what is the big benefit of this? It's not a single point analysis anymore. You're looking at the full field advantage. So that allows you to now adjust your tool parameters like your binders, your dies, and your support plates. You can adjust your press parameters. Maybe your die recipe is wrong. Maybe you need to adjust it to get a good part to match your FVA, which we're going to speak on a little bit later on. But you can make your quick changes in your tools. It's a huge benefit. So what you can see here in the pictures are, from your tool to your image acquisition point and to your final result, which looks like a finite element model, but that's the actual measurement. That's real world measurement that we're looking at here. The typical applications that we're going to be using this for are material acceptance. Again, we're going back to those spot buys that we talked about. You really need to understand, is this current material performing the same as the previous coil that you used? Series production ramp-ups, this is a big one. As you change materials, as you go through your production runs, you really want to understand that your part is behaving the same way so you get good parts, better quality all the way through your production runs. Again, problem solving, material variations, process parameters, these are all typical things that you need to know, but now you're looking at it from a full field perspective, which is a very huge benefit. A lot of R&D applications can be utilized here where you can see what kind of prototyping you're getting and how it's responding to what the FEA is supposed to be doing, and verify that directly within our software. This is a very big benefit of the Argus system. Now, how does the Argus work? The measuring principle behind it is that we're going to etch a regular dot pattern before forming. You have a few different options on that. You can do electrical chemical etching, which has been the industry standard, or you can do laser marking, which is now going to be a unit that we are releasing and introducing today to you. This is autonomous laser etching robot. This allows you to basically set it and forget it. Hit a button, let the robot etch any different area that you like perfect every time on any type of material, or you can do printed dots. The system measures the deformation of the dot pattern due to the forming sequence. This is similar to circle grid that measures the elongation of one singular hole or circle on the part. We're measuring the center to center distance of every one of the dots on the part at the same time. So again, more of the measuring principle is that it's going to do the computation of the 3D coordinates of all the dots. So we're measuring displacement and calculating strain of every dot on the part itself. And what you're going to see as the results are 3D coordinates. You're going to automatically calculate the major and the minor strain, and you're going to get material thickness based on those values. And it's going to be automatically compared to the forming limit diagram, which again, you can get the forming limit curve from the ARAMIS as we just discussed in the previous slides. And this will validate and optimize your numerical forming models. Again, this is real world, so now you can compare this directly to the theoretical FEA model. So John's going to go over some summary benefits here. So John, I'll hand it back over to you.
Thank you, Yanni. With the Argus laser etching robot, we have the ability to now be able to quickly and efficiently etch the part without any wasted man hours, as well as a safer, simpler task. But it also makes for a perfectly etched panel every time, and it doesn't really matter what material it is. Everything from steels to aluminums to high-strength steels, and sometimes that are very difficult to etch by hand. The laser just adjusts its power to meet the requirements. And this really helps in truly understanding the increased accuracy, reliability, the increased accuracy requirements of the formability of panels, especially in our lightweighting world, and really helps us truly understand the nonlinear strain paths, which AutoForm 2020 will help with. And this will lead to overall Industry 4.0 improvements in the technology, as well as the technology being, much more green and environmentally friendly, safer for operators without having to use chemicals, et cetera, and having it totally autonomous so that operators can either etch specific areas they're interested in quickly and efficiently, or just set it, forget it, and have it etched entire panels.
Thank you, John. So we'll go through more about the Argus system a little bit here and what it entails. The Argus system is a certified measuring camera and lens. It's certified by GOM to do exactly what it's supposed to do, meaning that it is certified within a tolerance, since optics is our world. It comes with certified scale bars that are NIST certified, so they can be put through your ISO standard for qualification on an annual basis, biannual, whatever you want to do. A mobile high-end laptop and a wireless image transfer, which allows you to be roughly 30 feet away from the computer, and as you take the images, it wirelessly transmits all the data back to the computer, so the operator doesn't have to download anything at all. Here's a quick video to show you how the Argus works. So you're going to see here that the operator is going to set up a part. He's going to take images from 3 different levels to triangulate the data. And once he gets those 3 different levels, he's going to rotate the part. As he's taking these images, notice on the left-hand side of the screen here, these images are coming into the computer and getting computed automatically. This is what I was talking about not having to be next to the computer the entire time. It's all wireless. There's nothing tethering him to the system itself. Now, moving on to the afterward. Once the images are in the system, they are automatically computed within the software, and you can see the result on the screen. And as we're going through here, you're going to see that the result on the screen looks very similar to an FEA result, but these are actual results of major strain and minor strain and thickness reduction. You'll see that it starts off with a theoretical flat blank, and then it shows you what the images were calculated to be. And you'll see here he's showing major strain. It's in a 3D world, He's going to toggle it to the minor strain here so you can see the results of a different strain here. And again, you don't have to reshoot the part. It just is calculated automatically, and then thickness reduction and so on and so forth. There are many different other strains within the system that automatically come with it if you want to see something like MESI strain, displacement in a specific vector direction. It's all here, and you'll see that in the lower left hand, or the lower right hand corner, I should say. It's all put automatically to the forming limit diagram. So the operator doesn't need to hunt for any failure points. They can see what it's doing to the forming limit curve. So going into the Argus scan box, our Industry 4.0 method, it's the automated Argus. So what this means is that similar to the ATO scan box that is out in the industry now, we now have the availability for the Argus scan box, which is easily to be programmed through what's called the VMR, which can be programmed once for each part and then rerun again automatically for continued measurements on the same panel. So many people do annual reporting on these panels, and it is very time consuming. Once you record it one time, the program is saved within the computer, and all you have to do is set the part back up and hit the go button. The system will automatically take the images and then output the data. And this is just an example of what the part would look like as opposed to your traditional on-the-table measurement. We'd be leaning the part up vertically, almost like at a 30-degree angle, and let the robot move the table around and take the images. Here's an example video of in the field testing that we've done on an Argus scan box, and you'll see how the table is rotating to take our 4 directional shots. And then as it's taking the different angle shots for the Argus, this timing of doing this measurement went from roughly 15 minutes doing it manually to roughly a 4-minute cycle to do it with the robot, and you'll see the output on the right side of the screen. So John, I'll pass this over to you.
So the power of the scan box is not only is it faster and more efficient, and will automatically measure your part perfectly every time, but it really saves a tremendous amount of time for the operator to be able to run. It's very simple to train on, and it makes for perfect measurements every time. And so engineering, formability team will always get the same kind of results every single time. And so it's really not only a time saving, but higher quality measurement than you were previously doing. And it just saves time from, wasted time of bad scans, bad measurements, and you're just getting that first run formability measurements fast and efficiently. And this kind of precision is really required for this Industry 4.0 formability, where, lightweighting is causing formability to be much more critical than it has been in the past. So be able to lead to more highly accurate formability measurements. And the savings is tremendous from a man-hour perspective as well as a quality perspective. Yanni?
Thank you, John. So some of the Argus applications, like we've talked about, one of the big ones is monitoring the process stability of a series production. We can import the FEA data directly into our system and do a best fit alignment and then what's called a manual pre-registration. Basically what we're doing is moving the Argus measurement into the same position of the FEA model, which is usually in car position or die position. Then what the software will do is calculate the surface geometry deviation. So you have full control over the alignment and the accuracy of that alignment. So the user has that control to say, you know what, I want to measure or hold it to this feature, which I know is not changing, which then will give you a nice deviation map correctively. The alignment is important because the system maps the nodes from the FEA directly onto the Argus measurement. It's like a blank canvas. So you'll see here that wherever the alignment is, the nodes do a straight line measurement directly down onto the surface. So it's really important to get a nice alignment so you know that you're getting a one-to-one comparison on each node for major strain, minor strain, or thickness reduction. Then you'll notice here it does the calculation of the differences between the FEA and the measurement. So you'll see the top one here is the Argus measurement. The middle one here is the simulation result, and the bottom one here is the comparison between the two. This is important because now you can understand and see what the differences are and then report this back to your simulation team to make smarter models as you move forward. And you can see here that we can do a verification of boundary conditions. We can do a knowledge building for and transfer all this information upstream and optimize the simulation process. This is really important because, as we mentioned, this is the real world measurement that we're measuring. This isn't theoretical anymore. Here's a nice example of comparing the equivalent strains of before the trimming process. So this is the draw tool of the measuring data at the top, the FEA at the bottom, and then over to the right side, you see the comparison between the two. I will discuss this little red area here at the bottom in a few minutes, but I want you to understand that this is a comparison, so you see the differences between the two. The important thing to remember is which one you're subtracting out and which one is showing you high or low. We're not going to get into detail about that, but we'll take questions on that later if there are any. Here's another comparison of the material thickness. So you can see thinning to thinning here of the measurement data, the FEA data, and then the comparison of the two to see is the thinning matching between the two data sets. This is very important because based on the material criteria within the simulation, they're putting in these variables and you want to make sure, is the tool performing the right way or vice versa? Did the tool perform differently but still safe? And how can you pass that information upstream to the simulation team? Now here's a cool one. A question comes up very often is, can we only measure the draw station with the artist? The answer is no. You can measure the part all the way through every station, and this is a nice example of after the trimming process, after the final trimming process. You have the measurement data, the FEA data, and then you have the comparison again. Why is this important? This is important because once you make a trim, the final trim, an addendum, something might spring out, something might change, and you want to make sure that everything is holding true all the way through the forming process, the trimming process, and everything across the whole tool until it gets to the final part. Here are some examples of geometric boundaries, and this is what I told you I would talk about in a couple slides. So sometimes you have different blank sizes and that have no access to beading. And cause different friction conditions. So you see the two, the measurement data, FEA data, and again the comparison, and you have this little red area here. This is a primary example of showing you that the FEA data had more blank size than the actual part did. This could be an issue because what if on the part that area did not get to the bead which needed that extra pull to form the part? That could give you a completely different forming condition that you might not have realized. The Argus can show you this binder pull-in. It can show you how much blank it's actually using, and actually this might be a good material utilization tool to understand what you do and don't need. Here's an example of the missing draw beads in simulation. So you can see the measurement data has a little bit of an area here in green. The FEA data doesn't show it because I believe the FEA data doesn't have the draw beads in there. And you see the comparison difference where you see more pull on the comparison between the actual to the FEA data. And this is what you can check very easily with the Argus system. And John will talk about some more benefits.
And so when we have better computer models, the AutoForm 2020 will now really be including nonlinear forming effects. And this really helps in truly understanding how the parts are being formed, especially with the new lightweighting materials that we're utilizing, and the requirements for much higher precision measurements and formability to be able to meet the requirements of producing a good part. And because of the lighter materials, nonlinearity in the forming process has a much larger influence than it has had in the past. But once you have, from a cost savings perspective, better designed parts form correctly the first time. You're not going to be going back and forth trying to solve little problems that were caused by, maybe not taking all the conditions into effect, especially nonlinear forming issues. But better designed parts just makes better parts, which makes a whole process work much more efficiently, and the cost savings can be literally in the hundreds of millions of dollars, and would be able to lead to more accurate parts, leading to less downstream problems, less and fixes that need to be done, less vehicle structural recalls, less warranty issues, and basically happy customers. Yanni?
Exactly. So here's some examples of Argus applications for tool optimization. You don't always have to shoot the entire part and check it. Sometimes you just need to fix a hotspot and move on and keep everything going because we all know time is money. So here's an example of a zinc-coated corner of a part here. It was a hotspot, so before the tool optimization, you see that little red spot here. And in most cases, the red does mean failing, but red doesn't always mean failing unless you realize where it's at compared to the forming limit curve. In this case, you'll see that it is above the curve. The operator can pick those points and really understand an actual solid number of how far above that line you are, so we can tell the tool maker how far to fix it. We don't want to lose it in just grinding and you just blow it out of the water, where in this case you know where you are. You can quickly have a panel etched right behind this one, and once you do the work on the tool, shoot it again after you hit it, and you can see now everything is safe, completely under the material curve, and move on with the knowledge, the full knowledge, and this metric to compare it to the next future hit that you do, knowing that you are now safe. And again, this is another one for monitoring process stability. From a press run to a press run, and the difference of when you're starting, when you have a good zero reference panel, as we're going to call it, from a production one that you're doing today, a production one you're doing in a few weeks, you always want to make sure you're getting consistent parts across the board. One of the great benefits that the Argus affords you is that you can keep that model as your reference panel and compare that to future production runs to make sure you have process stability. And keep that as a tracking metric from prototyping into the first build, into production runs, and onward for the life of the tool. This is a huge cost savings to really understand where you are, not just to say we're running a safe panel, but you never know where you really are. And as John had mentioned earlier, the nonlinear strain paths that are occurring within these forming process are very questionable. You don't know what's going to happen. It could cause failures, and you might not know exactly how safe you are. The Argus will let you know that during your production run. So it's a really good thing to have and a good knowledge to have as you're moving forward for better quality parts. Here's an example of what I kind of said earlier about before the trimming process and after the trimming process, and being able to track these critical areas. So you'll notice there's that critical area before the trimming process that's causing some kind of strain in that little area in the middle of the part there. You'll see how it's above the line on the forming limit diagram. And then after the trimming process, when it's cut, that goes away. So that strain might not be a problem that you have to worry about, but this is a cool way that you can track it, a very nice and easy way to track it on a full field basis, to know that that little area that got trimmed out, that released the part, that is no more strain, did not affect any other areas as well. So the full knowledge is here, and that's how you can track it. So now we're going to talk about some ARAMIS for press deflection, and I'm going to hand this over to John to talk a little bit about this.
So when we're using ARAMIS, we're going to use high-speed cameras now to measure the die and the tool, so that and the press, so we can really understand how all of it's working together in a good operational perspective. And so with ARAMIS press deflection, we're going to use a stereo imaging ARAMIS tool like we had before, but from a larger field of view. And we're going to use some target dots to put onto the part so that we can then track those points with high accuracy. And here's an example of a die coming in and watching it go in through the process and making sure that it's properly aligned going in. With this shear, we were having some problems with the shear cutting properly, and just from this measurement, we found some bearings were bad in the part, causing a shudder during the cutting process and producing bad parts. This is a high-speed measurement, and we're looking at the various points, comparing the bottom of the tool with the top of the tool and seeing how the two are aligning and moving relative to each other in the X, Y, and Z directions. We apply these tools to truly understand the relative displacements of the press and the tool components, and really creating a baseline of operation. Once we have this baseline of operation, we can then really understand the press performance during the operation, station-to-station performance validation, the effect of different materials, especially high-strength and ultra-high-strength steels, on the tool itself and on the press, making sure that it's all working appropriately, and recording that die recipe and tracking the ongoing metrics for better panel qualities, and really knowing what the variables are causing an issue or not. And with these measurements, we can do preventive maintenance, really understand and solve press issues, tool issues, and make for a very efficient operation, solving problems rapidly and just making sure that all your tools are working appropriately. Yanni?
So in conclusion, as you can see, like we started with the agenda, it came full circle. We started with the ARAMIS for material properties, showing you as the incoming material, we can test it to really understand the proper N values, the proper R values, and having the proper forming limit curves to know that we're using the right data as we're checking our tools. And then going into the Argus patterning, which increases our accuracy by using our laser etching Industry 4.0 formability tool, allows us to have good quality parts coming in to get good quality data coming out, which will eliminate problems down the road. And then going into the Argus measurement for formability of not only understanding what the part is doing from simulation, but getting the real world measurement using a full field tool. And then also having that data as a metric to check it for production runs, and then going into the ARAMIS for press deflection, which is now the full story of what we're doing. It's a full circle result. They all work together hand in hand, because even if you're still not getting a good measurement, maybe it is the press that's causing the problem, but this is how you'll know with all this data, all this knowledge put together, gives you that full spectrum of Industry 4.0 and that nice result that everyone needs to have for good cost savings and as we move into the future using this technology. So with that, I want to say thank you for your attention. I believe we're going to open it up to a live question and answer. So John, thank you again for participating. And we appreciate your time. Thank you.